see what I have next. Okay, so yes, so moving on. So I'm going to go straight into now. Well, another example will come up about empirical formula, molecular formula. But these two learning goals, right, I'm going to be kind of combining these in calculations. So mass percent of each element in a chemical formula, okay? Because if you think about it, the mass percent of each element in the formula will be the same for the empirical and for the molecular, right? There's no way to tell the difference when you're just doing mass percent. I'll show you that. So for example, a compound that contains only carbon, hydrogen, and oxygen is 48.64% carbon, 8.16% hydrogen by mass. Oh, and they didn't tell us the oxygen. That's why I got confused, okay? What is the empirical formula of the substance? Well, hopefully it's obvious. If not, that's okay. But hopefully it's obvious that this all has to add up to 100, right? Because if we're saying the compound only contains carbon, hydrogen, and oxygen, and we were given the percentages, then we know that we can say, for example, 100 minus 8.16 minus 48.64, and then I know the rest of it has got to be 43.20. And notice, because these all have to add up to 100, it's all about the decimal place, right? This 48.64 has 2 decimal places, 8.16 has 2 decimal places, and now 43.20, I need 20 with 2 decimal places. Okay, so how do you calculate this? How do you do this? Well, what I want you to get used to when you see these percent by mass problems, so in percent by mass, assume you have 100 grams. Okay, you can make that assumption. And thereby, if I assume that I have 100 grams, then I know that I have 48.64 grams of carbon. I have 8.16 grams of hydrogen, and I have 43.20 grams of oxygen, right? So that's very easy to all of a sudden now convert those percentages into masses. And then now what I want to do is convert these to moles. And you'll see why in a moment, okay? So I know from the table, so I've got to go, right, grams of carbon in 1 mole of carbon. The table tells me it's 12.011 grams of carbon in 1 mole. For hydrogen, grams of hydrogen in 1 mole of hydrogen. The table tells me 2.016 grams in 1 mole. Okay, I think I keep writing 1 twice there. 1 mole hydrogen, 1 mole, let's write this out so you can see it a little bit better. 1 mole hydrogen. Okay, 43.20 grams oxygen, and then I know I've got to go grams of oxygen to moles of oxygen. So in 1 mole of oxygen, there's 16.00, okay? And so then now, when I convert these, 48.64 divided by 12.01 is 4.050 mole. Let's write that better. 4.050 moles of carbon. When I do this calculation for hydrogen, I get 8.095 moles of hydrogen. And when I do this calculation for oxygen, I get 2.700 mole of oxygen. So what does all of this mean? Well, what this means is that this compound actually would have a formula C4.050H 8.095O 2.700. And that's a big no dice. Because I can't have like fractions of atoms. I can't have 2.7 oxygen atoms. But the proportion, the ratio of these elements is exactly these numbers. 2.7 oxygens for every 4.05 carbons. 8.095 hydrogens for every 2.7 oxygens. Those proportions are correct. So how do I make these whole number quantities? The way that I do that is by dividing by the smallest number, okay? So in this case, oxygen is the smallest number, so I'm gonna divide that by 2.700. We call that the least common denominator, right? And that would give me 1.00 moles of oxygen. If I divide this by 2.700, I get, it actually works out to be 2.998 moles of hydrogen. And if I divide this number by 2.700, I get 1.500 moles of carbon. Okay? So now that means my formula looks something like this. C 1.500, H 2.998, O 1.000. That's not bad. That's getting a little bit better, okay? But I still can't have that 1.5 carbon. So what I'm going to do is say multiply by 2. That's going to give me C3, H 2.998. That's safe enough to assume that's 3. But if I multiply by 2, it's going to become 6. And then multiplying this by 2 gives me O2. And this is my empirical formula. And the reason why it's my empirical formula and not my molecular formula is because I don't know what the molecular mass of this compound is. I know what the ratio of elements should be. It's 4.05 to 8.095 to 2.700, which is actually the same as 3 to 6 to 2, which is kind of cool. But all the same, I don't know what my molar mass is, so I can only say that this was the empirical formula. Okay? So now what about another problem? All right? A white powder is analyzed and found to contain 43.64% phosphorus and 56.3% oxygen by mass. Those definitely add up to 100, right? And now they tell me the molar mass is 283.88 grams per mole. What are the compound's empirical and molecular formulas? Well, let's do it. Remember, we'll start by assuming we have 100 grams. So I'm going to say 43.64 grams of phosphorus. And I want to convert that into moles. The molar mass is 974 grams of phosphorus in 1 mole of phosphorus. And when I do that calculation, I get 1.409 moles of phosphorus. And oxygen, that's 56.36 grams of oxygen. And I know in oxygen, there's 16.00 grams of oxygen in 1 mole of oxygen. And when I do that, I get 3.523 moles of oxygen. And so I have to find the least common denominator out of this, which I do by just assuming that the 1.0409 is the least common denominator. And that gives me 1.00 moles of phosphorus. And when I divide this by 1.409, I get 2.500 moles of oxygen. So I can't have P1O 2.5, but I can have P2O5, right? That's the same ratio. But now, is this the molecular formula or is it the empirical formula? Okay? So the way I find out is by calculating the molar mass of this. Okay? So the molar mass of P2O5 I can calculate by saying 2 times the mass of phosphorus plus 5 times the mass of oxygen. So that's 30.974 times 2 equals plus 5 times 16 equals, oh, this comes out to be 141.95, let's say, grams per mole. Well, look, they told us the molar mass was 283.88. But I'm getting 141.95. So what's going on with that? And we'll recognize that my empirical formula and my molecular formula have to be related to each other by some whole number quantity. So what happens if we say try to multiply by 2? So what if we say instead P4O10? And let's calculate the mass of that. What do we get? Okay. 4 times 30.974 equals plus 10 times 16 equals, oh, look at that, 283.896. This says 283.88. Perhaps I used, not enough sig figs or whatever. Doesn't matter. It's damn close, and that's good. And so this tells me that this has to be the molecular formula because it gave me the molecular mass, the molar mass, and this has to be the empirical formula, okay? And these all contain the same proportion, the same ratio of elements by mass. But to distinguish the molecular formula from the empirical formula, we have to know what the molar mass of the molecule is. Okay, folks, that is it for chapter 3. This was kind of our first really big fat chapter with a lot of calculations. Chapters 1, 2, and 3 are going to be on the exam. Make sure you're going through those learning goals. Make sure you're going through the question banks. I'm going to release the free response question bank soon. In the meantime, please make sure that you're getting through those question banks and learning goals. And if you have any questions, don't hesitate to come find me in office hours. All right, folks, I'll see you in discussion.